Okay, now it seems eventually we can start. Just let me see if everything is okay. Yes. Okay, so if you remember, we introduced the notion of integer powers for matrices, and now we continue the lesson. So what is the next natural step? The next natural step might be a good idea to see what are the rules of these powers. Yes, for example, in numbers, we had if I am working with positive integer powers, if a is a number and raised to power n multiplied by a to power n, of course you have this rule. Yes, and then you also have this rule: a to power m to power n is equal to a to power m times n. We also had some rules for divisions, but we haven't studied any divisions for matrices, so we don't consider those rules for powers. But another power rule is this one. If I have two numbers multiplied together, and if you want to raise it to power n, then what you have is a to power n, b to power n. So that's also another rule that we learned for numbers. Okay, so we want to see which one of these rules, if any, uh, can be transferred into matrix theory. Okay, so what's your idea? Do you have any idea? So do you expect that these formulas also work for matrices? Yes. So for example, if I have a matrix a to power 2 multiplied by a to power 3, first of all, do you think this is completely trivial that this should be equal to a to the power of 3, a to the power of 2? In principle, no. Yes, because a to the power of 2 is completely different matrix. You cannot find a complete relation between a and a squared. A to the power of 3 is also a different matrix. So then I am facing two different matrices. So there is no guarantee that a to power 2 multiplied by a to power 3 in principle is equal to a to power 3 times a to power 2. But in this case, we will see that yes, the answer is yes, and these two are the same. Yes? Exactly. So this formula is correct. So a to the power of 2 times a to the power 3 is equal to a to the power 3 times a to the power 2, even though you need to be careful when you interchange, when you commute matrices, because matrix multiplication is not commutative. But do you think I can also write this equal to a to the power of 5? The answer is yes, because if I ask you what is a to power 2, do you remember what we talked about? A to power 2 times a to power 3. A to power 2 means a times a 2 times, but a to power 3 means a times a times a 3 times. Because of associativity, I really don't need to care about pair of brackets. I can remove the pair of brackets. This is not ambiguous. And then if I ask you how many A's you see here, you see 5 A's, and there is a better name for a times by itself 5 times, and that is a to power 5. Yes? So a to power 2 times to a to power 3 is indeed equal to a to power 5. Okay, so let me write this theorem officially. Let A be a square matrix and let alpha be a real number. Then, okay, first part, I can write number 1, a to power n m times a to power n is equal to a to power n times a to power m is equal to a to power m plus n. Yes? And number 2, if I have a to power m to power n, then it becomes a to power m times n. That's also true. And number 3, if I have the number alpha multiplied by my matrix, and then I want to raise it to some power, say n, then I can raise the number to power n, I can raise the matrix to power n, and then multiply them. I think the proofs are simple, yes? You just write them n times and then multiply them, and you see that. But what do you think about this formula? You see, in this theorem, I haven't mentioned it here. So might be this is not correct in general. But can you, first of all, why do you think, in principle, we should be a little bit suspicious about the validity of this? Yes?
Because they are reorganized when you do that. In that one, it's A, B, A, B, A, B. In that one, it's A, A, A.
Yeah, so we are interchanging them, yes? So this is the reason that we should first of all be a little bit suspicious about that, why this formula might not be correct. For example, if I write a b squared in numbers, what is the meaning of ab to the 2? It means that I have to multiply ab by itself. But when I am dealing with numbers, we know that there is no difference between b times a and a times b. So in that case, instead of writing ab, I can write a, and I interchange these two. So it becomes a, and then b goes next to it. It becomes b times b. But of course, a times a is a squared, b times b is b squared. This is the crucial part. So commutativity is actually being used to be able to go from this side to that side. Associativity is used because I can remove the pair of brackets and put them around these two, but also commutativity is used because I can interchange these two, yes? But because we lose in general, we lose commutativity in matrix theory, matrix multiplication. So it means that there is no guarantee that this formula is a valid formula, yes? So be careful. These formulas are exactly like the formulas with numbers, but this formula works with numbers, but in general, it doesn't work with matrices, okay? So let me write first a remark. So part 1, first of all, let me ask you about this. What happens if I have the negative of a matrix to some power n? Of course, here I have been a little bit careless. I have to mention that m and n are non-negative integers. I don't know if we can have time to reach what happens if we have negative integers. But for the time being, these are non-negative integers. But you will see in the future, even if they are negative integers, these formulas are still valid. But still, we don't know what's the meaning of a to power minus 2, for example. Yes? So here, again, here, n is a negative, is a non-negative integer. So how can I write this? According to this formula here, minus a to power n, what is the meaning of minus a to power n? It means minus 1 times a to power n. According to this formula, it becomes minus 1 to power n times a to power n. So be careful here. This is not this formula I am using. Here, one of them is a number, the other one is a matrix. So this formula looks like this formula, but this is not that formula because one of them is a number, the other one is a matrix, yes? So what is the answer? Minus 1 to power n sometimes becomes 1 if n is even, sometimes becomes negative 1 if n is odd. So this means that this is equal to a to power n itself if n is even, and it becomes minus a to power n if n is odd, yes? So this is very trivial from this part of the theorem. So if you have a matrix, it's exactly like numbers. What is the feeling is exactly the same. But let me write number 2 here. in general, the formula a times b to power n, the relation, it's better to write it, the relation is not valid. Okay, I don't know how to write it, is, so let me change my color and write not valid. So since the validity of this relation relies on commutativity of multiplication. Yes, but we know that multiplication of matrices in general is not commutative. But you have seen some examples of matrices that commute. Yes, sometimes AB is equal to BA. So in that cases, A times B to power n is equal to A times A to power n times B to power n. Yes? So this is something that I want you to know. And let me now solve some problems together so that we can go to the next stage. Let me write an example here for you. So let A be equal to this 2 by 2 matrix, -2, -2, 2, and 0. Determine A to power 41. You will probably study in the course Linear Algebra University a systematic way of raising matrices to high powers. Okay, I'm not going to teach that one to you because probably we will not have time. But A to power 41, still you can solve it, even though you don't know that systematic method, because some matrices are designed in some way or planned in some way so that if you calculate the first few elements, the first few powers, might be you can find a pattern or somehow you can solve the problem. Okay, so at the level of your lesson, if you are facing with extremely high, this is extremely high if you don't have calculator or computer, if you are facing extremely high powers of a matrix, it means that probably you need to calculate the second power or at most up to three or fourth power, see the pattern and use that pattern to solve the problem. Yes?
Yes, that was mine.
Yeah? Okay, so this is one idea. So let us try to see how it works. Okay, so let us calculate a to power 2 in this case. A to power 2 means multiply this matrix by itself. Yes? Okay, can I get something out of this? Let us calculate. So what is the first entry? -2 should be multiplied by -2 is +4. -2 multiplied by 2 is -4. So do you agree with me? The first entry is 0. And what is the next one? It becomes +4. And this one, -4. And the next one is -4, yes? Am I right? So I get this matrix. It's not that clear what is going on, so might be we have to do once more. So let us calculate a to power 3. You know that in general it matters I multiply a by a squared or a squared by a, but we learned here that different powers of the same matrix definitely commute. So don't need to be worried about that. So it doesn't matter if you multiply a squared by a to get a to the 3 or a by a squared to get a to the 3. So let me multiply it by a times a squared. Okay, so a times, you can do the other way around to see that the answers will match at the end, even though intermediate steps are different. So a is the original matrix minus 2, and 2, and then I have 0. I multiply it by a to the 2, so it becomes 0, 4, 4, minus 4. And then what you do, you calculate this product once more. So it becomes minus 8, and then it becomes minus 8, positive 8 becomes positive 4. Is that right? And then 0 and 0, it becomes 0. What I get there is 2, is 8, it's just 8. I don't know. I don't like it that much. We don't see any pattern here. Did I make any mistakes?
I think top right should be here instead of
Here? Okay, so let me double check. So it's 0, minus 8, that's correct. Minus 8, positive 8, so you are 0. Yeah, that's 0, thank you. And what about this one? That is also 0. And then I have 2 is 8. Yeah, that's correct. Yeah, this is correct, yes? But now I don't know what will happen if I multiply it once more by 2. Okay, let us check once more. Because, pardon? Here? If that's minus 8, it's better, of course. Here? Here? No, this one multiplied by that one, 0, 0. It's 0.
Oh, yes, I have a minus.
And then here multiplied by that is 8 and 0. That's correct, yes? So let me just do once more. Hopefully I have designed the equation, because systematically solving these things are a little bit different. So a to the 4 means I multiply a once more by a to the 3. But what is a? A is minus 2 minus 2. And 2 and 0. And I multiply it by minus 8, 0, 0, and 8. So let us see how this will go. So the first one becomes 16. Please check my calculations. Minus 16. Yes. And then minus 16 and 0. Do you agree with me?
Yes.
Hmm?
Wouldn't it be faster to calculate a to power 2, a to the power 4, a to the power 8, a to the power 16, and then convert
No, that we need to do something. This is not going to work because it doesn't come back to somehow to some pattern itself. Might be this diagonal one is a good one. Yes, because we know how to raise diagonal matrices to power. So let us stop there, if you don't mind. It's better to stop there. I was thinking that might be another pattern emerges. Might be I have done some mistakes, but I think still we can solve this problem. Yes, because do you remember what was the rule of raising matrices? Diagonal matrices to powers are easy. Yes, do you remember? If I give you a diagonal matrix, this is a diagonal matrix. Yes, if I ask you to raise it to high powers, if I give you this and I ask you to raise it to power 1000, it is still easy. You just raise this one to power 1000 and this one to power 1000, and you are done. So let us start with that one. So we realize that a to the power of 3, we found something for it. Yes. So if you see, I can factor an 8 out. So then I will get minus 1, 0, 0, and 1. Of course, this is unfortunately not the identity matrix, but it is not hard to start solving the problem from here. Agree with me? This is a to the power of 3. I factored 8 out, so I am facing here. But I want to calculate a to power 41. According to the rules that we learned today, I need to write this power 41 somehow related to power 3. So what is this? I can write it as a to power 3 to power 13. Do you agree? So far, I have 39 powers of a. I need 2 more, so I have to multiply it by 2, a to the power of 2. Yes? So this is the rule that we learned today. This is the rule that we learned today. So hopefully you agree with me. A to the power of 41 can be written in this form. Yes? And then a to the power of 3 is this matrix. So instead of a to the power of 3, I put this matrix. So it becomes 8 multiplied by minus 1, 0, 0, 1, this to power 13, multiplied by a squared, but I already calculated the a squared. A squared is this matrix. So this is 0, 4, minus 4, and minus 4. Then I have to calculate this. But calculating this is easy, yes? Because according to this rule today we learned, alpha multiplied by a matrix raised to some power, I can raise the number to that power, and I can raise the matrix to that power. So this is this combination that you see here. So what I do, I would write 8 to power 13, and then I would write minus 1 to power 13. So let me write a step by step. Then it becomes this matrix to power 13. Okay, and if you don't mind, let me a factor of 4 out here. Calculation becomes simpler. So it becomes, this is not mandatory, of course. Okay, but now 4 times this number, this is a big number, so I don't need to bother. I just write it like this. And what I have to do, I have to calculate the 13th power of this matrix, but this is a diagonal matrix. Raising diagonal matrices to high powers is extremely simple. What I have to do is just simply raise the main diagonal to power 13. And then I have this matrix left, but this calculation now becomes very simple, yes? Because this is just 4 times 8 to power 13, and this minus 1 to power 13 is just minus 1, and then I have 0, and then I have 0, 1 to power 13 is also 1, and then I have to do this multiplication. So you see, it was not that horrible. It was easy to solve this problem in this way. And now I have only to multiply these two matrices and then I am done, yes? So what I do, I will calculate. So let me write this number in front for the time being. And then I start multiplying these two matrices. So minus 1, 0 multiplied by that gives me 0. Minus 1, 0 multiplied by that gives me minus 1. And then this one multiplied by that gives me minus 1. And the other one is also minus. And then if you want to, this is a big number, I just multiply it inside. So this becomes 0 minus 4 times 8 to power 13 minus 4 times 8 to power 13 and minus 4 times 8 to power 13. So this is what we get for this problem. Okay, so I realized that I made a mistake. You didn't catch my mistake. Because when I was designing, this is a nice problem, but of course there is a flaw in this calculation. You didn't catch that. I should have been more careful. So you learn a lot of things actually by solving this problem in a wrong way, but do you see what's the flaw? Yeah, I was a little bit surprised because I remember when I was designing this question, I wasn't thinking in that way, even though that's much nicer. Uh, the problem is that when I move this from here to here, I forgot to put this negative sign there. Yes, so this problem is simpler. So yes, pardon? Yeah, so this minus 4 should be here. But then if I multiply, what will happen? It becomes 8, yes? So this one multiplied by that one, 0 and 8. This becomes 8. And now everything is much simpler, yes? And then when I multiply this by that, it becomes 0. When I multiply this by that, it becomes 8. So it was finished here. Of course, you learned a lot of things by doing that mistake, yes? Uh, You learned good things here, so you calculated in this way, but more or less we are done there because this is 8 times the identity matrix. It was not identity matrix in the beginning, but still it was doable by these techniques. But let me now solve the correct problem. Sorry for that. Okay, so this is now what we get is a to the power of 3 is if I factor 8 out, what is left for me is the identity matrix. Yes? Now this is much simpler now. Of course, the tricks are the same. I have to use the tricks. So I would write a to the power of 41 is a to the power of 3 to the power of 13 multiplied by a squared. But a to the power of 13 is 8i times to the power of 13 multiplied by a squared. But a squared is that matrix 0, 4, 4 minus 4. Yes? So this is a squared. But then it becomes a to power 13. But identity matrix to power 13 is the identity matrix. Identity matrix multiplied by that is the same matrix. So it becomes 0, 4, minus 4, minus 4. This was more tricky, but it's doable. You see, at least we use this idea that if I have a diagonal matrix raised to some power, it is easy to calculate that. And then if I multiply that, let me write the answer here. What you get, the correct answer to this problem was this, which we messed up actually. So here, so it is different from that answer that we get at the end. It's, yeah, there is a minus sign difference from that one, okay? So anyway, is that understandable? So at, yes? Sorry, may you repeat it again? Yes, it is better. Yes, why not? You are right. Because this is also a, yes, it's better. Yeah, thank you. So, by the way, let us do that. So this becomes equal to 0. This is 2 to power 2. This is 2 to power 39. It's much nicer to see it in that way, yes? This is what you mean, yes? Okay, let us see. Is there any pattern, nice pattern going on? No. But it is much nicer to write it in this way because at least you see 41 appears here and 41 is here. Yeah, this is a better way to writing, definitely. Thank you. Okay, it's not understandable. So if you have a high power of a matrix, it's tricky. Okay, so you need to know how to calculate that. At this level, you have to calculate one or two or at most three of them so that you can see what the pattern is. Sometimes you find a pattern, you need to have a guess and then use mathematical induction to prove that. If you remember, we solved some of those problems. But apparently, this doesn't seem that there is a good pattern going on. I don't know. Do you see the pattern? Is there any pattern emerging? So second power is this one. This is the first power. So can you something guess what happens for a to power n? If you can have an educated guess for a to power n based on some simple calculations, then you can write a generic formula and then use mathematical induction to prove that. Of course, if you can't find that pattern, this is a much nicer way because not only you can solve it for a to power 41, but you can use it for any power of that a. This is more stronger, but it takes time. Sometimes these patterns are not that easy to come up with. For example, a to power 2 is this number, is this matrix, so there is some relation to 2 to some power, and a to the power of 3 suddenly becomes that. And after that, it follows a different pattern, yes? So for first one and the second, so you see the third one suddenly becomes the identity matrix. And then I don't know if you can come up with a pattern, yes? Anyway, now let me give you another example. Is that understandable? Okay. So have this in your mind. If there are high powers of some matrix in the exam, either mathematical induction should be involved or calculating some low powers and finding a relation so that you can raise it to some power after that. And if you remember, do you remember what was the idempotent matrix? We talked about that last time. That was also good to know. What is the idempotent matrix? Do you remember? Yes? A squared is equal to A itself. And what was the property? If a matrix to power 2 suddenly becomes itself, and I ask you, can you cook up another? Because one possibility is to consider I. I is, of course, idempotent. I squared is I. But do you think I is the only one? Let us, by the way, that was an exercise. I don't know how many of you have thought about that. So let us consider a 2 by 2 matrix, which is not the identity matrix, but it is still idempotent. Yeah, zero matrix I also consider trivial. But any other one, let us quick it up. So let us try to find some. I would say that I am looking for a matrix A, B, C, D, such that A squared becomes equal to A. So let us calculate this. A squared means A, B, C, D multiplied by A, B, C, D. This should be equal to the matrix itself. But on the left-hand side, I can calculate something. It becomes A squared plus BC, AB plus BD, and then AC plus DC, and finally BC plus D squared. So I want to make it equal to A, B, C, D, and of course I want to make it a non-trivial example. So you see that you have a system of equations. So what is the system? A squared plus BC. I don't want to solve it, but I want to guess another set of numbers which will work for me. So then if I factor a B out from here, A plus D should be equal to B. And then I factor a C there. A plus D times C should be equal to C. And finally, BC plus D squared should be equal to D. So I will face this system of equations if I want to cook up idempotent matrices. But of course, this is only idempotent matrix for 2 by 2 matrices. There are 3 by 3 matrices, 4 by 4 matrices. It becomes more involved because the number of equations would be much higher. Okay, so can you see any trivial, any non-trivial example here? Yes? Not exactly. Either B is 0 or A plus D is 1. Yes? So that's what I'm saying. So for example, let us consider these scenarios. Yes? Let us consider that neither B nor C is equal to 0. I don't want to solve this problem. There are different cases to consider, but at least I want to come up with a non-trivial example. So if B is not 0 and D is not 0, assume, I don't know, because I just want to see, can I come up with a non-trivial answer? A non-trivial answer is better to consider these non-zero, yes, because this becomes more non-trivial. Okay, so if B is not equal to 0 and C is not equal to 0, then I am on the safe side. As you said, I can divide by B, I can divide by C. Otherwise, I cannot divide. So if I do that, the second equation will give me A plus D is equal to 1. And then the third equation also gives me this. Yes? So, yeah. And then I have A squared plus BC is equal to A squared. No, is equal to A. And then I have what? D squared plus BC is equal to D. Let us subtract these two case by case. Yes? A squared minus D squared. And BC are gone. This becomes A minus D. Yes? Here, I can use a conjugate pattern to factorize this. But of course, this is highly trivial now. Because A plus D is 1. And then if I multiply that, it becomes a minus d is equal to a minus d. Okay, so let us now, if we want to do something, it is better to do it here. So this is a number. Now, can you guess a bunch of four numbers, a set of four numbers that satisfies this condition, this condition, this condition, this and that? So for example, the first thing comes into mind, let us check, let us make a to be 1/2, d to be 1/2. Let us see if it works, yes? This satisfies this condition. But if I put a to be 1/2, this becomes 1/4. When I move it to the right, it becomes 1/2 minus 1/4. So it becomes BC is equal to 1/4. Do you agree? Is that understandable? Okay, so what is another guess for B and C? Both of them to be 1/2, yes? So apparently this should work. So apparently this is one of those matrices which is not the identity matrix. Even if I factor 1/2 out, what is left for me is this matrix. Okay, but if we have done everything right, it means that this matrix to power 2 is definitely equal to itself. Okay, so let us check. A squared is this matrix 1/2, 1/2, 1/2, 1/2, multiplied by 1/2, 1/2, 1/2, 1/2. I don't know, is it the case or not? Is it? Do you think? This matrix multiplied by that, 1/2 times 1/2 is 1/4. 1/2 times 1/2 is 1/4. If I add them, it becomes 1/2. But this is exactly the same scenario going on. So it becomes 1/2, 1/2, 1/2. So this is also an idempotent matrix, which is not trivial. Of course, here you might ask, is this the only one? If you really want to solve this problem in full detail, you need to answer all possible solutions to this system. It is good to think about, can you categorize all possible 2x2 idempotent matrices or not? So you need to work on this system of equations, try to see, can you find all possible answers to these equations or not? Yes? Yeah?
If you put either B or C to be 0, aren't you forcing yourself to use an identity?
We can check. So for example, if I put b equal to 0, then this automatically, so which one? Both b and c equal to 0. Uh, so you need to check. If I put b equal to 0, this is already clear. But if c is not equal to 0, then a plus d is equal to 1. And then bc is equal to b is 0. Okay, if b is 0, what happens? This becomes a squared is equal to a. So the answers are 0 or 1. Yes, these are the possible answers. If I put b0 here, b0, this the same story for d. This means that d is either 0 or is equal to 1. Okay, but you said that b is equal to 0. What happens for c? We have different scenarios going on because we need to consider only this one. If a is equal to 0, then d becomes 1. Okay, so yeah, might be these are the only cases if b is equal to 0. Yeah, I don't want to delve into this problem. If you're interested, you need to solve. This is a nice problem, by the way, to categorize all idempotent 2x2 matrices. But my point was this. And my point is that, by the way, this is also a deviation from numbers. If a squared is equal to a, what you can conclude about a, put two possibilities. Either a is 0 or a is equal to 1. But you see that in matrices, this doesn't work. A squared is equal to itself, but this is neither the identity matrix nor the zero matrix. So these kind of strange things can happen in matrix algebra. Okay, but I wanted to talk about high power. So if now I ask you what is a to power, which year is this? 2000, yeah, 21. So what is the answer to this one now? It's a. We learned that, we proved this by mathematical induction, that if a matrix is idempotent, any power of that matrix is also equal to a, not just a squared. The reason is clear, yes? Because a to the power of 3 is a to the power of 2 times a. But you are telling me that a to power 2 is equal to itself, so it becomes a times a. it becomes a squared, but again, a squared is a. So the third power is also equal to a. So this is also something that you need to know. For high powers, might be this is the rule. We will come back to these kinds of problems later. Okay? Any questions so far? Okay, now let us give you another example. These are simple ones, but I want you to get used to this new algebra. So we are working with an algebra that we have lost commutativity, but all other things are actually preserved for us. But you see that some odd things can happen even in this simple case. So example, this is a very simple one, but I want you to see how do you solve the problem. Uh, let A and B be square matrices of the same order. Let me clean this. And let C be the product of B by A. Write this expression, this B, A, B in pair of brackets to power 5 times A in terms of C. Okay? So you start thinking about this so that I can have time to write another example here. Is this question clear? So B and A are square matrices. This is definition of C. This is an expression written in terms of A and B, but I want you to write it in terms of C so that this one is equal to some expression in which C is the only matrix involved. Okay, this is a simple one, but that might be a little bit tricky. I hope that I remember how I designed it myself. Okay, but this one shouldn't be hard for you. If A and B were numbers, probably the good starting point is to write A5, B5, yes? But am I allowed to use A5, B5 here? That was one of the exceptions that I told you don't fall into this trap. If these are matrices and you don't know anything about if these matrices are commuting or not, which you don't see it in the text of the problem, you are not allowed to presuppose that A and B are commuting. So you need to stick to this uh, idea that they are not commuting. Okay, so the question mark is this, B, A, B to power 5A. Okay, so what is the natural thing to do? Yes? 5 times. So this is the only way that we can do that. Exactly. So this becomes B, AB times AB times AB, AB, and AB 5 times. Is that right? And then at the end, I have an A there. Okay, then what? This is the only way, yes? Use associativity, yes? Take this pair of brackets and put them around the first two, yes? Put this pair of brackets and put them around these two. Without interchanging, without commuting anything, the way that I read this sequence is BA, 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 BA up to then. But how many BAs are involved now? Agree? BA, this is this one, 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 and BA, this is this one. So, but BA is given to be C. So this is C times C times C times C. 1, 2, 3, 4, 5, 6. So this becomes C to power 6. So this is just C to power 6. You see, this algebra is very simple, but you get used to working with numbers. You need to change the way that you have used to think when you are dealing with matrices. It was very simple, but that was the idea. Is that clear for everyone? Okay, these kinds of problems could be really, really hard. You know, there are some of these problems that I don't know. I spend even 1 hour, I cannot find a relation. So because it's not something intuitive. You need to be smart to find the patterns and things like that. But this is not, of course, the hard thing. My goal is to understand these things are not valid. So can from this equation, so this, let me read this one for you. A and B are square matrices of the same order. For some reason, even though we don't know, is it order 2, is it order 100, 1 million, we don't know. But we know that A times B is equal to A, and simultaneously B times A squared is B. You might ask how we know that such matrices exists in the first place. We don't know. We are assuming that if this is true, we want to follow this is the case. Okay? Okay, so first of all, I want you to understand this. Can I conclude? If I write this, this is what I want you to know 100%. Can I conclude B is I, like numbers? Can I do that? No. This is important. Why? Because I told you, if you remember, A times B equals to A times C. in general, I am not allowed to conclude that B is equal to C unless this has an extra property which we don't know yet. Okay, so you are in that case, if that I can simplify, but still we don't know anything. So in general, I cannot simplify. Do you remember? Multiplicative cancellation in general is not valid. This is multiplicative cancellation. Do you see that? Because instead of A, you can imagine A times I and then simplify A from both sides and conclude B is equal to I. So if you go from here to here, in principle, you are using cancellation law, multiplicative cancellation law, which in general is not valid. So don't think in this way in this problem. For the same reason, from this second one, BA squared B, can I conclude that A squared is I? Again, no. So these are the things that you need to start changing your habit with numbers. Okay, so this is not the correct solution, because if I could conclude this, for example, if I conclude this, the last one is very simple, yes? Because if you can conclude from this that B is I, of course B squared is I, B is also I, so I am done. This is oversimplification of the problem. I am not allowed to solve it in that way because it is not. Okay? So, and if this is true, this is also simple. Because if a squared is a, I multiply both sides by a, this becomes a cubed, this becomes a, and I am solving this. If you solve it in that way, you get 0 points, yes? Because the whole point is that to realize these algebra are for numbers, not for matrices. Okay, so this, let me just keep it like that. Okay, do you have any other suggestions? Let us concentrate on this one first. So my assumptions, let me put them in front of my eyes. I have AB is equal to A, and I have BA squared equals to B. These are my assumptions. I am sure about these two pieces of information. Now my question is that, can I show that A to power 3 is equal to A? Okay, yes?
We can square AB and then put it into equation 4.
So from here, you mean? So let me follow you. You are saying that AB is equal to A, and then you say that I square both sides. This is possible, because if two matrices are equal, it is clear that the second powers are also equal. Then what?
Then I take AB squared and put it into the in place of A squared in
Okay.
the equation for B.
You are not answering this one. Are you answering this one?
Yes,
Okay. So just tell me, what should I do then? You will take this one and put it where?
into B times A squared.
Here.
Yes.
Okay. Okay. You are right. So you are saying that BA squared is given to us to be B, and then you say that you take this A squared from here and put it here. Is that understanding? Yeah. So this means that B, instead of A squared, I can write AB, and then to power 2 is equal to B. Okay, and then what?
I expand it.
This one?
Yes.
Okay, so you expand this, it becomes B, A, B, A, B.
Then
This is equal to B still, okay?
then I use associativity to rewrite it as BA times BA times B.
Exactly.
And because in the it says that
How do you continue then? You see, this is not trivial. You need to think. So I will come to you. Okay, so let us see. Alec will actually finish it or not.
yeah, I think I've done something wrong.
Oh, no problem, no problem. But what you have done is completely valid. That is the hard part of these kinds of questions. Whatever we do is completely valid. What you told me is completely valid. The problem is that it doesn't work. This can be these kinds of problems can be really hard. Okay, so this method doesn't work, so we need to do some trial and error to find that one. Let us concentrate again here. Okay, so still the question mark is left. A to the 3, I want to show that this is equal to A based on these two assumptions here. And of course, our own knowledge of matrix theory so far. Yes? Yes? A, A, A. Yes, so let me write left hand side. The middle A. Am I allowed to do that? Middle A by AB, if you want to, not BA. Because A, B is equal to A. If you want, I can do that for you. Okay, so if you mean that I put this A here, this A there, but instead of the middle one, you decided to put AB. Yeah? Yeah, so up to here is correct, but then if you can continue yourself. You see, it is tricky, not that easy.
It hurts when I can do mistakes.
Yeah, yeah.
Oh yeah, yeah. Mr. Novak.
Continue.
Replace the first one instead. The first A with the
Okay, okay. So let us try. Instead of this one, you put AB, AA. Okay, then what? From here to here, you mean? Okay. Okay. So you mean what? What should I write then? Okay. So what? A parentheses BAA. Okay. Yes. Yes, that's correct. Okay, but you don't need to make it so hard. You don't need to write AA. Yes. Yeah. Yeah. That works. Yes. So you see, it's not trivial. So let us now we have a better way to do that. So what you said, instead of writing it 3 times, let us write it as A times A squared. Yes. This agree? And instead of this A, you told me put AB. So instead of this A, I put AB. Let us do it step by step. So what I have done, instead of this A, I put this package. Is that right? And then I have associativity. Associativity means that you can take a pair of brackets from this pair and put them around the second pair. But then suddenly some nice thing happens, yes? Because BA squared is also given to us in the problem. So it means that instead of BA squared, I put A and I put B. Why is that? So I have replaced this package with this one. Is that understandable? But what is AB? AB itself is also given to be equal to A. Is it true or not? This is not my job, yes? My job is to work it out if this is true. So this is AB, and this is equal to A itself, and this is equal to the right-hand side. So you see, based on these two given properties, and based on which property we used, here we use this rule of power, and then we use associativity. We were able to show that A to the 3 has to be equal to A. If you say these two things are correct, then I conclude that A to the 3 is also equal to A. Yes.
I realized I hadn't actually made a mistake in the writing. But
Okay.
when I tried to understand what I did, I had to split parentheses, so I didn't know which A I had replaced.
Yeah.
Because it just became.
Yeah. So I don't know. I lost the battery. So yeah. Hopefully he can continue watching the video. Yes, I want to finalize this problem. Okay, so can you come up with the other one? You see, these are tricky problems. The next one is to prove this one. I don't know. I want you to give some time to think about it yourself. Yeah, because I have seen many of these problems. I spent, I don't know, hours, and at the end I cannot solve. Yeah. So yeah, let think about it, make it completely complete for both cases, and then at the last 10 minutes we start solving those. Okay, both of them. Okay, both of them. Okay. Let everyone thinks, and then I will come back to you. So if Alex, you have the solution for three of them, I will ask. Uh, yes. So you say that you have the solution. Okay. I think the last one is harder if I remember that because I usually put them in order. Of course, this is a little bit subjective thing. Yes.
The last one.
Yes. Just let me talk to him. Sorry. So, Malcolm, the computer battery is dead, so I cannot probably continue because we have only 10 minutes. I want to finalize this problem. I don't want to spend time on putting everything there. Okay, but you can think about this problem and then you can see the video after that when I uploaded it. Okay, sorry for that. You're welcome. Bye. Okay, let me see what is going on here.
So Carl, can you just give me the second one and I will ask you the third one and let us finalize the problem if I, yes. So how should I do the second one? Okay, so just describe your solution so I will follow you. So you want to prove this one. Let me write it in front of our eyes here. This is my question mark. So what's your strategy?
Well, first you can expand it.
Okay, so you start from left hand side, yes? So left hand side is equal to BA squared, but BA squared cannot be written as B squared A squared because we don't know if they are commutative, but we can still expand this in this way, yes? And then,
Then you use associative to group together middle A and middle B.
yes,
And then you can write that as A.
this one,
Yes.
yes, AB is equal to A, so then it becomes BAA, which is BA squared, yes, thank you, that's working. This is BA squared, and BA squared is given in the problem to be B. So this is B, and this is the right-hand side. So that was also simple. But I want you to learn this way of thinking, abstract thinking. Okay, are you ready for giving that the last one? Okay, so tell me what to do. So let me write this in front of our eyes. Our goal is to show that B squared is equal to B. Okay,
Yep. So you know that BA squared equals B implies that BA squared equals B squared.
okay, so you want to start not from the left. Okay, you want to manipulate that piece of information. No problems. Let us see if it works. You are saying that because this is given to be equal to this, it means that the second power of the left-hand side is also equal to the second power of the right-hand side. So far, so good. Then
So then we know that the left hand side is BAA.
here,
Yeah, but no, B squared equals B. We take the left hand side and rewrite it as BAA.
uh,
Using that.
this one. So
Yeah.
I don't understand. You want to keep B squared the same?
Yeah, yeah, keep.
Okay, so it means that on the right hand side I will keep B squared. Let me write them. Let me write them in this order. It's easier. If you want to go step by step, let me write them vertically. So you say that I raise both sides to power 2. That's completely valid. And then you say that I keep the right hand side as it is. What should I do for this?
Just rewrite it as BAA.
Okay, so BAA, you mean this?
and then we use associativity to write BA and in parentheses AB.
This one?
Yeah, and we know that AB equals A. So we can write it as B and then A4, I guess.
Yes.
And then using the previous answer, we know that 3 A's is the same as 1 A.
Yes.
So we can rewrite that as B.
You want so you want to combine these three or these three?
It does matter.
Yeah, it matters.
I don't know if we take last 3, I think. Yeah.
Okay, so last three. Oh, okay, so might be that doesn't matter. You are right. So you mean this one, yes? So okay, so b squared and then what?
We replace A
Cubed.
cubed.
Yeah, because a cubed, we showed that this is equal to a. So you write, instead of a cubed, you put another a. But then this becomes what? ba squared is equal to b squared, yes? But what is ba squared? ba squared is b. So this means that b is equal to b squared. So that is one possible way. But of course, if I were you, you don't need to expand these a's that much. You have expanded to make sure that everything works fine. But then when you are finalizing it, you can go back and polish it a little bit so that don't expand what you don't need. Okay. So I don't think that you really need to expand that lot. Do you need? So for example, if you just let me just follow your rules. But let us see, really, do we really need to expand these a's from the beginning? So for example, why not, instead of ba squared, let me just write ba squared. This doesn't work, you mean, yes? So on the right hand side, I have b squared, but then I will take these two. So here probably I need to expand and put one a with b, and then a squared there, yes? Yes. And now you see that b is a, so then it becomes ba. This a by that a, it becomes a cubed. So you don't need to expand that much, but that's exactly the same idea. You might have found another way, but you need to check that everything is valid or not. But you see, this is non-trivial thing, and there is no intuition behind that. I don't know. So if you want to solve a calculus problem, might be you see the graph, draw the graph, try to visualize it in somehow to come up. But this is pure logic, or I don't know if it is logic or not. You just need to play around so that you can get the right combination that will work. Otherwise, it's not possible. So I remember that once I was trying to solve one of these problems. I don't know. After 1 hour, I I couldn't solve it for after 1 hour. I might, if I can find it, I will bring it for you. You can test your own way of doing that to see it works or not. But at the end, I don't know. 2 weeks, 3 weeks later, again, I came back to the problem. After 2 or 3 hours, I was able to solve that. And I don't know, still know, is it the optimized way of doing that or not? I mean, there is no way to think, okay, I want to follow this logic to reach to the answer. That's I'm missing. I don't know. Can you cook up with a logic? Of course, there is a logic behind that. I cannot say this is a random process that Alex did it. There are some logics behind that, but they could be extremely hard if the logics are not so simple. The people who design that. Okay. Any questions? Uh, yeah, there is a little bit of time here, so let me also mention this theorem. At least, even if I don't have time to formally state it, but I want you to understand what is going on. So I don't know, did I talk about this symbol for you or not? Called commutator. I don't think so. Okay, so this is very simple. This means AB minus BA. Of course, in numbers, there is no point to define the commutator because the commutator is always zero, yes? AB minus BA is also equal to zero always. But in matrix theory, it makes sense to define what we call the commutator. Okay, so this is something I don't know why I didn't talk about. I want you to know about this sometimes. Uh, sometimes they call it Lie product. Lie is a mathematician. Okay. Lie product of two matrices means multiply two matrices in different orders and subtract them. The whole combination is called the Lie product. Okay, but now I want to ask you this question. If two matrices are commuting, if A commutes with B, what do you think about A2 and B? In principle, A2 is a totally different matrix, yes? If I have a matrix, I multiply it by itself. If the entries are randomly chosen, there is no guarantee that A squared follow nicely from A, yes? It is completely a new matrix. Now I am telling you that we know that A and B commute, meaning that I know that AB is equal to BA. Do you think that I can conclude that A squared is also commute with B? In other words, do you see that this is true? A squared commutes with B if this happens. So I am telling you, I start with two matrices that I know for some reason they commute. Now I am asking, take one of them, raise it to power 2, it becomes a new matrix, keep the second matrix as it is. The question is that, do you think that this new pair of matrices also commute?
Yes. Yes.
Why? Yes?
We can rewrite a squared b as a times b.
Yeah, exactly. So you mean that I start from the left-hand side, I write it as A times B, and because I know it's associative, let us forget about pair brackets, and then
Then I can commute the second a with b, and then
which one? This one with B, exactly. I can commute these two, so I am keeping A, and I'm just commuting them. And then what?
then I commute
Once more.
yes.
Yes, I commute once more. It becomes A, B, but another name for, no, oh, I reached to this one, sorry. I have to commute these two, yes?
Yes.
Yes. These two I commute, it becomes A, and then it becomes BA squared. Okay, so you see that if A and B commute, A to the power of 2 also commutes with B. But what do you think about A to the power of 3 and B? It seems the same logic will work eventually, yes? So if I start with A3B, I can write it as A, B, and then I can replace these two. So I have two A's and BA, and then I can replace these two. It becomes AB, A, and then I replace these two, so it becomes BA. So then it becomes BA to the power of 3. Okay, so in principle, A to any power commutes with B from this trick. But if you want to prove it, you need to prove it by mathematical induction. So I want you to prove it as an exercise. We know that A and B are commuting. Show that any power of A commutes with B. So in the Lie product way of expressing this, I would say that if the commutator of A and B is equal to the zero matrix, show that A to power n, the commutator of A to the power of n and B is equal to 0 as well. Okay, now let me make the question a little bit different. So if I have A and B commuting, what do you think about A to the power of 2 and B to the power of 3? What do you think now? If A and B commute, I take one of the matrices, raise it to power 2, I take the other matrix, raise it to power 3, and now I have two new matrices, and now I am asking, do you think that they also commute? Yeah, it seems yes. Why is that? Because you know that there is no specific role to A and B here. We say that if two matrices commute, any power of one of them commutes with the other one. You can read it in this language. Okay, now you are telling me that two matrices commute. So the second power of this one commutes with this one itself. And now I have one matrix, another matrix, one matrix commutes with this one. Any power of this one, including the third power, also commutes with that one. So if you can solve this problem with one of them raised to some power, you can also raise different ones to the power. So let me write these rules. If A and B commute, then you can conclude that any integer power, any positive integer power of A and any positive integer power of B, they can be the same, they can be different. This is also equal to 0. And if I want you to understand that, not just to memorize that, this is easy to see. If two matrices commute, any power of one of them commutes with every power of the other one. Okay, so I told you that because this matrix algebra is not trivial, whenever we have pair of commuting matrices, I think it is better to categorize them and send them or send this to our memory so that we can use it later if we want. Okay, we can stop here. Thank you.